Hi, Assalamualaikum warahmatullahi wabarakatuh. We are from Group 4 and we will be presenting the fourth experiment, which is vapor compression refrigeration. Our group consists of 5 members, which is me, DIYANAH, NOOR AMIRA, NASREEN AINA, FIZRI HAZEEM, and NOOR ALAZIM. I will proceed with the objectives of this experiment. First and foremost, this experiment is to determine the coefficient of performance (COP) for vapor compression cooling system. And also, this experiment conducted is to investigate the effect of flow rate of condenser on the compressor power.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is FIZRI bin ISMAIL and I am from Group 4. Today I'll be explaining about the theory and application of experiment 4. Okay, the compression refrigeration cycle is a thermodynamic cycle to generate refrigerating effect through 4 stages of a closed system, which consists of compressor, condenser, expansion valve, and evaporator. Vapor compression uses a circulating liquid refrigerant as the medium, which absorbs and removes heat from the space to be cooled and subsequently rejects that heat elsewhere. This process requires W, which is work, to be supplied to the system. Okay, we move on to the next slide. Okay, in this slide, I will explain how this cycle actually works. Okay, for the first step, refrigerant enters a compressor as a low pressure vapor to be compressed, which raises the pressure, causing it to become superheated. Okay, next, it enters the condenser. Heat is transferred from the refrigerant to a flow of air. This heat transfer causes the hot vapor refrigerant to reach its saturated temperature, hence changing its state to a high pressure liquid. Okay, note that the diagram that we use are a little bit different from the lab manual, but the concept are just the same. The only things that differs are we use air as cooler, while in the lab manual use water as cooler. Okay, for the next step, the refrigerant enter the expansion valve, which expand the liquid refrigerant and lowering the pressure on the outlet. Besides, temperature also reduced in this step. Okay, lastly, in a cool, low pressure liquid state, it is ready to enter the last stage, the evaporator, which the heat is finally removed from the space being conditioned. Fans are then used to blow warm air. Heat is absorbed by the cooler refrigerant, hence reducing the temperature in the conditioned space. Meanwhile, when the refrigerant absorbs heat from the surrounding air, it begins to boil and transform into a low pressure vapor. The low pressure vapor is subsequently reintroduced into the compressor, and the cycle begins again. This last slide just explains how we can find COP from 3 different formula. Okay, first of all, coefficient of performance COP can be calculated based on the following equation. COP is equal to desired result divided by required input. Next, for the refrigerator, the desired result is the heat absorbed at the low temperature and the required input is the net work into the device. So, COP is equal to cooling effect divided by work net in. And lastly, from figure 2, we can conclude that the heat absorbed at the low temperature is equal to Q2 and the net work into the compressor is equal to Q1 minus by Q2. Hence, our COP is equal to Q1 divided by bracket Q1 minus Q2 close bracket. Okay, I think that's all from me. We move on to the next presenter. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is NASREEN and I'll be explaining about this experiment apparatus and procedure. So here is the component in refrigeration cycle unit. Consists of evaporator, compressor, 2 valves, main switch, temperature indicator and temperature selected switch. These are the experimental procedure. First, the components: evaporator, condenser, compressor, expansion valves, watt meter, water flow in and out, and the flow of fluid R141B as depicted in figure 3 are identified. The thermometer for each position is observed and the vent valve is not blown out. When operation is launched, The valve and the water pipe are open as illustrated, and the water flow rate is set to the evaporator as 19 gram per second and the water rate to condenser as maximum. The cooling system is allowed to be stable at approximate 10 minutes and the parameter listed in table 1 are recorded. The experiment is repeated by changing the flow rate of water to condenser in between 0 to 20 gram per second. This experiment is repeated 4 times. When the operation is terminated, the device is closed by switching off the main switch. After 1 minute, the water supply pipes is turned off. The valves to the shutdown position is closed after 1 minute.
I am AMIRA and I will discuss about the results. So, based on this table, these are the results that we will gain in this experiment, which later we will discuss in the discussion. I will proceed with the discussion. The first one is to calculate the rate of heat transfer that occurs in the evaporator and the condenser for the 5 test run and discuss the results. For rate of heat transfer in evaporator or QL, we will use the formula of Q equals to M delta H, where the flow rate of evaporator for this experiment is constant for all 5 tests, which is 19 gram per second, which we will then convert to 0.019 kilogram per second. And for the enthalpy, we can get by doing interpolation based on T1 and T2 of every test using steam table. So here we can see how QL for every test will gain. And then we will get QL for test 1 equals to 46.23 kilowatt, test 2 is 46.21 kilowatt, test 3 equals to 46.18 kilowatt, and test 4 and test 5 are 46.12 kilowatt and 46.09 kilowatt respectively. Next, we will proceed with calculating rate of heat transfer for condenser QH by using the same formula Q equals to M delta H. But the differences are the flow rate of condenser for each test are not the same. After calculating, we will get QH for test 1 equals to negative 43.66 kilowatt, test 2 equals to negative 38.67 kilowatt, QH3 equals to negative 28.95 kilowatt, QH4 is negative 19.27 kilowatt, and QH5 equals to negative 9.60 kilowatt. Continuing our discussion, which is the objective of this experiment, we will now determine the coefficient of performance COP. The rate of heat transfer of evaporator QL and the rate of heat transfer of condenser QH are magnitudes, which means they have positive values. Therefore, in order to calculate coefficient of performance of the refrigerant, we will use the above equation, which is COP refrigerant equals to modulus QL divided by QH minus QL. Then we will get COP for test 1 equals to 0.514, test 2 0.544, test 3 0.615, test 4 and test 5 0.705 and 0.828 respectively.
Hi, my name is NOORDIN. So this time I will be explain about the second question in the discussion for experiment 4. So the first discussion state that we need to explain the effect of changing the condenser flow rate of T1 to T6 to compressor power. So we need to discuss and draw the graph based on the result obtained. So the first graph is we need to plot temperature versus condenser flow rate. So based on this graph, we can observe that the temperature and the flow rate of condenser are related as temperature affect the flow rate, where the temperature increasing when the flow rate is decreasing. But this statement is invalid for the T5, as we can see it is dropping at the end, maybe because by the errors occurs when they're handling the experiments. So the second graph we need to draw is compressor power output versus the flow rate of condenser. the compressor power input increased from the test 1 to test 2, which is from the 244 watt to 274 watts. But then it continues decreasing from the test 2 to test 5. This is maybe because of inconsistency in the data, in the data, maybe because the error occurs during the experiment. So in order to gain accuracy in the data, we need to take the average value of the temperature as it affect the value of other data.
Last but not least, for the conclusions, the result obtained allowed us to plot the graph of temperature versus condenser flow rate. It was shown that the temperature increasing when the flow rate decreasing, while for test 5, the temperature decreasing because it may caused by some errors that occurs while managing the experiment. Furthermore, the results also allowed us to plot the graph of compressor power input versus flow rate of the condenser, where we can observe from the graph that the compressor power input increases from test 1 to test 2, then continuously dropping until test 5 due to some errors. Therefore, the coefficient of performance COP for vapor compression cooling system is achieved and shows that the increasing value of COP for all 5 tests. That's all from us. Thank you.